This is by Professor David Smith, and he has spent his academic career in the University of Oxford. And he co-founded the Oxford project to investigate memory and aging, OPTIMA, which he's director from. And, well, he's deputy head of the Division of Medical Sciences at the University of Oxford and fellow of the Academy of Medical Sciences. And he will talk us about designing medicines for Down syndrome. And I think he will also, well, explain us part of the results of Professor Helga Refson. That is somewhere, I think, no? Okay, there she is. And she's professor of nutrition at the Institute of Medicine, University of Oslo, and visiting professor at Oxford. And with David Smith, she has successfully trialed a vitamin treatment to slow the rate of brain atrophy and cognitive decline in people with mild cognitive impairment. So thank you, David.
Thank you for the introduction. I must correct the statement. I'm no longer deputy head of medical sciences in Oxford. I retired from that in 2005, and I've been doing research full-time ever since. So thank you very much, Peter, for putting your trust in me, who has never worked on Downs. My only paper with Downs involved is a letter to the Lancet pointing out that people doing tests for spina bifida using our acetylcholinesterase isoenzyme had contaminated the electrophoresis kit with the culture medium for the cells that they take out in amniocentesis looking for trisomy. So that's my contribution. So why did you ask me, Peter? I think you asked me because we've been working on Alzheimer's. I've been working on Alzheimer's for 27 years. And because Alzheimer's disease, or a dementia very much like Alzheimer's disease, is the end stage, if you like, of Downs, it may be relevant that we've found some ways of perhaps modifying the disease process, and I'd like to end up by telling you about that. But before that, I have to address this question towards designing a medicine for Down syndrome. And the sort of pessimistic view is this, that Down syndrome is due to an extra copy of human chromosome 21 and is regarded by many in both basic and clinical research as too complex a challenge for any effective pharmacological or other interventions. I got that from the web, so people think that. Ladies and gentlemen, what I'm going to try and show you is that that is not true. So what are the challenges? Well, we've heard about that, and basically what I'm going to do is rush through a kind of summary, well, attempt to summarize what the other distinguished speakers have said, not having heard what they said when I made the slides. So, you know, a bit of imagination there. So these are the challenges. We have basically developmental disorders, which we know about. Intellectual disability is the one that's very obvious, ID for abbreviation. And then we have the later life disorders in Down syndrome, which develop a bit later on in adulthood and as they age. And of course, dementia of the Alzheimer's type is one of those. If we're thinking about therapy, it's very important. I think Mara made this point, and perhaps others did too. If we're thinking about therapy, then we have to distinguish these stages, because it might be that you need different therapies for different stages. So for development in utero in the first few years of life, we may well want a completely different kind of intervention to deal with these early genetically determined stages. When it comes to adult stage, some of the functional deficits in adulthood in Downs may be amenable to therapy, and I'll talk about that. But of course there we have to start with animal models. Then finally, the deficits associated with aging, notably dementia. There, I think the challenge is similar to that for Alzheimer's disease. And the big question there is, can we modify the disease process rather than just treat the symptoms? So let's look briefly an overview of the challenges for the developmental disorders and the functional changes in the adult. And These are popularly and generally thought to be due to overexpression of genes on the human chromosome 21, and those are the numbers which you can glean from papers from authors in this audience. There are at least 200 genes occur on the chromosome, of which 164 are code for known proteins, and maybe others, of course, unknown. The candidate genes are numerous, as Mara and others have said, the candidate genes for causing the harmful effects, and I've mentioned some, listed some of those there. But we have a very perceptive remark by Kathleen Gardner from Denver. Amelioration of intellectual disability in Down syndrome could require the regulation of the expression of many of the human chromosome 21 genes. To do this directly would probably require multiple drugs. I think we have to bear that in mind. We may have to develop a polypharmacy, at least for the ID stage. The alternative approach is the unitary hypothesis, which it's human nature as scientists to seek for. In my field, Alzheimer's, it's amyloid. In your field, it changes about every 3 months. And the flavor, the unitary hypothesis of the time, as Mara made clear and Jackie, is the Dirk 1A hypothesis. And here's a schema. You don't have to be able to read all the detail, but here's a schema from Vergil and Frost, where they actually, show how from going from the trisomy 21 with the extra third copy of the gene for Dirk 1A, you can explain everything, including dementia. And of course, as we've just heard, the last three talks, the formation of, or the phosphorylation step that Dirk catalyzes is inhibited by the beta-carbolines like harmine and the compound that Jackie talked about that's present in green tea. So this is a very attractive hypothesis, and I'm not dismissing it, I'm just saying I'm wanting to alert you to the fact that this is a unitary hypothesis, and you must be a little bit wary of unitary hypotheses. So let's have a look now, what have we learnt from these mouse models? And to an outsider coming to this field, I was immensely impressed by the mouse models, compared with the mouse models for Alzheimer's, which I think are really rather poor. You have a very fine set of models that have been developed over the years. And what have we learned from these models? Well, there's a big slide, but I've learned quite a bit from them. First of all, that the cholinergic deficit in the mouse model can be reversed by administering nerve growth factor into the brain. Bill Mobley did that some years ago. Then we have the very interesting finding that a drug called minocycline, which as a pharmacologist I'd never heard of as an anti-inflammatory, but it does have anti-inflammatory properties. It's used to treat rheumatoid arthritis. It is actually a tetracycline and has antibacterial properties as well. But this drug rescues the cholinergic neurons, which are partly degenerated in the mouse model, the basal forebrain cholinergic neurons, partly degenerated. It rescues them, and it partly restores cognition. So that's a very significant finding. Then we have another study of Bill's, where the noradrenergic deficit, which is found in these mice, due to loss of nerve cells from the locus coeruleus and the brainstem, this deficit is associated with contextual memory deficit in the animal. And this can be reversed by the partial agonists of beta adrenoceptors. And that's a very interesting finding. Then we have this NMDA receptor story where memantine, an NMDA receptor antagonist, actually rescues memory deficits, work of Costa and other people. Then we've heard today about the GABA receptor story, and I don't need to say any more about that, except that GABA receptor antagonists, broad ones, like pentylene tetrazone, will actually reverse the deficits in long-term potentiation and in object recognition in these mouse models. Then we have the interesting finding that 5-HT reuptake inhibitors, or fluoxetine was the compound used, actually rescue the neurogenesis deficit in these mice. These mice show less ability to make new neurons in those parts of the brain which can form new neurons, and that has cognitive impact. And giving the fluoxetine actually rescued this. It's a really amazing result because it persisted for some time after the drug was taken away. Then we have the amyloid story, that a gamma secretase inhibitor, which lowers the beta amyloid level, actually improves memory in these mice. Then we have studies of MARA again, where the enriched environment in the mouse model improves cognition, but it was gender specific, and it didn't really last very long, but it's a very important result in itself, I think. And finally, a fairly recent study where exercise has been shown to rescue the neurogenesis deficit. And that, again, is very important because we can all do that. We don't, but we should. Let's have a quick look at the memantine model, because memantine is a drug that's licensed for the use in treatment of moderate to severe Alzheimer's disease, licensed around the world, so it could be used in humans tomorrow. And some of the first studies were done in Denver by Costa and his colleagues, where they found that acute injections of memantine into the mouse actually reversed the deficit in the fear conditioning test. Just 3 weeks ago, no, not 2 weeks ago, September the 2nd, he published online a very nice paper with the title "On the Promise of Pharmacotherapies Targeted at Cognitive and Neurodegenerative Components of Down Syndrome." And in this report, he described a clinical trial that he's doing in Denver, and I'll come on to that in a moment. Let's have a look at the clinical trials that have actually been started using memantine in Down syndrome. The one at King's College London is a randomized trial of memantine over a 12-month period, basically to assess the safety and efficacy in the prevention of cognitive decline in older adults with Down syndrome, some of whom had dementia. So in other words, they didn't go to the pre-dementia stage, they actually took people with dementia and they wanted to see if the drug would slow down cognitive decline. The funny thing about this trial is I can't find out anything about it. I've written to the authors and they haven't replied. According to the data on the ClinicalTrials.gov website, it was started in 2005 and was supposed to be completed in 2006, but we don't know the result. Then there's a new trial that's just been started in Denver by Costa and his colleagues, which takes 42 Down subjects of a younger age, adult, but not yet with dementia. And it's a 16-week trial to see if giving memantine will actually enhance long-term memory. They picked long-term memory as a good marker of hippocampal function. And I understand from his article that just came out that it's still in progress, it's nearly finished, and so probably within a few weeks we might know the answers. But I must point out that these two trials are asking different questions. One of them is asking, does it prevent cognitive decline in people who have actually got early Alzheimer's or Alzheimer's itself? And the other one is just looking for enhancement of long-term memory in the adult subject. So let's have a look now. The rest of my talk will be about the later life disorders, in particular, in fact, exclusively dementia. So are these later life disorders actually caused by the extra copies of genes on the chromosome 21? Or could they in part have other causes? I say in part because I don't doubt that the extra copies of the chromosomes are an important factor, but are they the only factor? Are there other possibilities? The current dogma, I guess, from the literature is that dementia in Down syndrome is caused by the buildup of beta amyloid due to the extra copy of the gene for amyloid precursor protein, and also perhaps by the extra copy of BACE2 and DYRK1A. Is this dogma true? Dogma is dangerous. You should always question it. The famous paper 25 years ago from Henryk Wyszynski in New York had this title: Discrepancy between Alzheimer-type neuropathology and dementia in persons with Down syndrome. And it's been widely confirmed since then. What they found, and this is taken from a review by Zygmunt, the plots, what they found that, and we've heard about this several times, that the prevalence, or the incidence rather, of Alzheimer pathology in the brains of people with Down syndrome starts really when they're quite young, 10, certainly 20, and has reached its maximum by the time they're 40. So basically, effectively, all Downs people by the age of 40 will have enough Alzheimer pathology in the brain for the pathologist to say they have Alzheimer's disease. And that's the important thing. It's not that they have amyloid plaques. We all have some amyloid plaques. By the age of 40, they will all have enough plaques in the right configuration for the pathologist to say, if you sent them the brain, this person got Alzheimer's. But it turns out that they don't have clinical dementia. That comes many years later. And as Jackie pointed out, by no means all Down's people will get dementia. The figure that's in this review goes up to about 70% at the age of 80, 90. So we have this dissociation, which Wisniewski pointed out, between the actual presence of a pathological diagnosis of Alzheimer's and the lack of the clinical correlation. There's a big interval there, as you can see, and the question that I think is absolutely important for us to answer: does this interval of about 25 or 30 years between amyloid deposition and the onset of dementia in Downs give us an opportunity to influence the process? That must be 20 minutes, not 40, I hope. Is that right? Thank you. I'm about halfway through. So is there any evidence from research on Alzheimer's disease for interventions which might slow down the progression to dementia? That's what I want to talk about now. Well, you might be surprised, if you don't know the field, to know that there's an awful lot of non-genetic risk factors that have been postulated to be involved in Alzheimer's disease. Not proven, but postulated. And here's the summary of some of the most important ones. It's quite a striking list. You notice that I've put some in red boxes, and those, of course, are all risk factors for cardiovascular disease. So this is perhaps one of the big surprises of Alzheimer's research in the last 10 or 15 years. We always thought it was different from vascular dementia. Well, it is different pathologically, but the risk factors are just the same as for vascular disease. So if you look at these non-genetic risk factors for Alzheimer's, quite a few of them are potentially modifiable, and there have been some trials. And on this slide, I'm showing the ones which are have gone beyond the observational study to actual interventions. So the ones in bold italic are those where interventions have indeed shown that they can slow down the progression to Alzheimer's disease. Some of the interventions are very small and need a lot of replication, but that's the list. Bear that list in mind when we look at Downs. The idea that there might be other factors than the genes that determine dementia in Downs is not new, of course, and it was perhaps one of the first people to express it. It was Nicole Schupf. But Ira Lott and his colleagues have also expressed it over the last few years. So let's look quickly now at the factors that might modify the development of dementia in Down's syndrome. These are the factors that I've found from the literature, and just to show you that there is some evidence here, I will quickly show you the evidence without criticizing or commenting on it. Gender. This is a bit controversial because some people don't find it, but in this study by Schupf, they found that the proportion of Down's people developing dementia was developed more earlier in men than in women. What I find very interesting is that the risk factor gene for Alzheimer's, the ApoE4 allele, also turns out to influence the risk of developing dementia in people with Downs. That you wouldn't really expect if it was entirely due to the extra APP, would you? And here's a very striking result where you can see that people with 1 or 2 copies of the 4 allele, they develop their dementia much earlier than the people with a 3-3, and the people with 2, allele 2, which is fairly rare, they don't seem to develop dementia at all in this study. Then we have cholesterol, which is a very interesting finding, that people with cholesterol above 200 have a greater risk of developing dementia. That's the vertical axis, is the hazard risk of developing dementia, compared with those with a lower cholesterol. So you might ask the question, what happens if you treat them with statins? And that's what happens. The people who were treated with statins had a much lower hazard of developing, risk of developing dementia than the people who did not receive statins. And then we have the finding of on the estradiol. This is bioavailable estradiol in blood, not total. And those with the low bioavailable estradiol had a greater risk of developing dementia earlier on than those with high estradiol. Beta amyloid, you can't forget it, of course. Then we have a finding that if you look at the change over time in beta amyloid levels, you find that people whose beta amyloid levels change over time, and the time base is on the x-axis, so it ranges from up to 8 years. Over this period, those whose beta amyloid levels in the plasma decreased had a greater risk of developing dementia. Those in the dotted line, where it actually increased, had the smallest risk. So what about oxidative stress, which is the very popular topic in Alzheimer's and also in Downs? Well, Ira Lott has just published, literally a few weeks ago, the results of the trial, which they did in 53 people with Down syndrome who had dementia, and they treated them for 2 years with alpha-tocopherol, which is a form of vitamin E, ascorbic acid, of course vitamin C, another antioxidant, and alpha-lipoic acid. Sadly, there was absolutely no significant cognitive effect of this treatment. But of course, what they took people who already have established dementia. And I think we've got to, although those are much easier to diagnose and categorize, we've got to try and move it a few years earlier to people who are on the way to getting dementia and hope to influence the process there. Then we've heard today from Rima that maybe in Down syndrome there's a hypomethylation status because the ratio of S-adenosyl methionine to S-adenosyl homocysteine is lower than in the control group. And Benjamin Tycho showed us that DNA methylation in a subset of genes was different in blood cells and indeed now in the brain from Down subjects compared with controls. And in some cases this was associated by changes in gene expression. Now, methylation status, of course, as we've heard today, can be altered by giving folate and vitamin B12 or betaine, which remethylates homocysteine to methionine. So what about trials? Here's a trial that Jill Ellis did, and I think Jill's in the audience there, published in 2008, where she took 156 infants with Downs who were under 7 months old. That must have been heroic recruitment, and gave them a tablet containing a whole lot of antioxidants together with folinic acid. And it was a nicely designed trial, a factorial design, so she could answer several questions. The treatment period was 18 months, and the outcome was the Griffith Development Quotient. Sadly, there was no effect of this treatment on the development quotient, either the antioxidants or, as a separate arm, the folinic acid. However, one thing that you notice from this trial, I hope Jill doesn't mind me saying so, that the doses used were largely in the range of the recommended daily allowance. And you can see the folinic acid was really quite low at 0.1 milligram per day. And here we have, ladies and gentlemen, a trial from the Institut Lejeune from Henri Lehoup, which came out last year. This is giving folinic acid, which is the 5-4-mile tetrahydrofolate, looking at its effect on the developmental quotient of children with Down syndrome. and they took account of the thyroid status. Here they had 87 Down's children aged 3 to 30 months. They were randomized to 1 milligram, notice, of folinic acid for 12 months. 10 times the dose of, 10 times the dose of the previous trial. In the intention to treat analysis, there was no significant effect. But in the per protocol analysis, they did find a positive effect of the treatment on developmental age. And that was even more enhanced in those who were treated as well with thyroxine, because a lot of these children are hypothyroid. And here the difference was in the folinic acid group, it was 59.5%, and in the placebo, 41.8%. So that's very suggestive that a form of folic acid can actually do something in that stage. What about dementia? Well, the question I want to end on is this. Does improving the methylation status slow down the disease process leading to dementia? How do we measure the progression of a disease like Alzheimer's? You can obviously, and most people do, use cognitive measures, but they are unfortunately pretty inaccurate. If I test your memory today and test it tomorrow, you'll probably get a different score. But we have to do those. You can choose a blood or CSF biomarker, and although these are very popular, no one has really shown much effect of trials on them. Or you can choose the rate of shrinkage of the brain. Now that is highly accurate. If you use volumetric MRI scans and modern software developed mainly by Steve Smith in Oxford, the Sienna method, you can get an accuracy of or an error in this method of 0.02%. So it's a very accurate way of following a disease progression. We did this in patients with mild cognitive impairment, which, as you've heard, is a sort of prodromal stage of Alzheimer's disease. They are not demented. They live in the community. The only thing wrong with them is that they have cognitive impairment that satisfies certain criteria. Just to remind you that the rate of shrinkage of the brain in the elderly, people perhaps over 60, in normal people it's about 0.5% per year. In those with mild cognitive impairment it's twice that, 1% per year. And people with Alzheimer's disease it's between 2 and 3% per year. So there's a gradation of atrophy rate as the disease progresses. And of course there's a tremendous similarity, as we've heard, between the later stages of Down's and mild cognitive impairment and Alzheimer's. And I think I'll skip this one as I'm running late, but I'll show this one, which is from Andy Simmons, where they looked at the change in volume in the left frontal cortex of controlled subjects compared with Down subjects over quite a long period. I mean, it was a cross-sectional study, and they compared the brain volumes. And you can see that between the age of 20 and 60, there was an insignificant rate of shrinkage of the frontal lobe in the controls, but in those with Downs there was a highly significant shrinkage of the brain, just like we find in Alzheimer's and mild cognitive impairment. Cross-sectional. Wasn't it, Andy, if he's still here? Yeah.
We didn't have a 40-year study.
No, you didn't have a 40-year study. We've done a 20-year study, but anyway, so what I'm coming to is homocysteine. Homocysteine is a marker for B vitamin status. The higher the the lower the B vitamin status, the higher the homocysteine. So it's a useful marker. And raised homocysteine has been associated, as a summary now, I can't go through the evidence obviously, in prospective studies, that means you take the blood before the person has dementia, with the initiation of cognitive impairment in aging, the conversion from cognitive impairment to dementia, the incidence of dementia and Alzheimer's in a population, the Framingham study showed that, an increased rate of cognitive decline in patients with Alzheimer's, and an increased rate of atrophy of the brain. So we need a clinical trial of homocysteine-lowering B vitamins to see that if it will modify any of these, and we chose the rate of atrophy. So just to illustrate, before I show you the trial, the striking effect or association of homocysteine and brain atrophy. Here we have 94 community elderly in Oxford who were selected not to have any cognitive impairment at baseline. We carefully excluded any with cognitive impairment. We asked them to volunteer to have brain scans over a 6-year period 5 times, and we did lots of blood tests and cognitive and everything. And so we were able to measure quite accurately the rate, with Steve Smith, the rate of shrinkage of the brain over this period. And this plots the change in brain volume per year over the 6-year period. Sorry, the numbers have got a bit shifted on the x-axis, against the quartiles of homocysteine in the blood at baseline. And you can see that there's a big effect, or big association. The higher the homocysteine, the faster the brain is shrinking. So those in the bottom quartile, it was shrinking at 0.62% per year. Those in the top quartile, it was shrinking at 0.98% per year. What have I just said? There's something in the blood that seems to determine the rate at which your brain is shrinking. Pretty amazing. So, of course, we asked, is it folate or is it B12? Because these are the main determinants of homocysteine. And it didn't seem to be folate, not in this population, but brain shrinkage was markedly related to the B12 level in the blood at baseline, and this is the result, where we're plotting again the percent change in total brain volume over a 5-year period against the plasma B12 level at baseline. And you can see that there's a strong relationship, that going from a high normal level of about 800 to a low normal level of about 200, you're almost doubling the rate of shrinkage of the brain. Now, the important thing about this result is that these changes occurred in the normal range of B12. The blue arrow shows the cutoff, which is used by the clinical chemists in Oxford to define deficiency. Levels below that, you get a report of deficiency. You send them a patient who's got a neuropathy or something and ask for B12, and it comes back at 300, and they say it's normal. Is it normal to have your brain shrinking faster at 300 than 600? I ask you the question. So, now we come to the trial. The question for our trial was, since raised homocysteine and low B12 are associated with an increased rate of atrophy of the brain, then will giving B vitamins to lower the levels of homocysteine slow down the rate of shrinkage of the brain? Very quickly, the design was on this slide, and Helga was one of the PIs with Robin Jacoby, a psychiatrist. So the question was, do B vitamins slow the rate of brain atrophy in those with mild cognitive impairment? We recruited 270 people living in the community from Oxford who were over 70 and had subjective memory complaints, and when we tested them, they had mild cognitive impairment. Randomized to placebo or a tablet made for us by Recip in Sweden, which contains 0.8 milligrams of folic acid, twice the RDA in England, 0.5 milligrams of B12, 250 times the RDA in England, and 20 milligrams of B6, which is 10 times the RDA. These are pharmacological doses, not nutritional doses. They were treated for 2 years. We did volumetric MRI scans at the start and the end, and of course, we had to do a power estimate, and we powered the study to detect a 20% slowing of brain atrophy by the B vitamin treated group using this Sienna protocol of Steve Smith, which is very accurate. We did, of course, have secondary outcomes of which cognitive and clinical changes were very much included. So we have a kind of matrix here for this trial. We have a treatment, B vitamins. We have the end result. We want to know the answer, but the trial wasn't really designed for that, cognition. But we have in between plasma homocysteine and brain shrinkage. So the first question is, does the treatment lower homocysteine? It was designed to, but of course if they didn't take their pills they wouldn't have. Well, it did. It lowered homocysteine by 32%. So the next question is, did the treatment affect the rate of brain shrinkage? And the answer is, it did. The mean slowing of brain shrinkage was 30% in the B vitamin treated group. So the main effect of the outcome of the trial is a highly significant slowing of the rate of atrophy by B vitamin treatment. We obviously did subgroup analysis, which we'd pre-specified. the most important one of which was, do baseline homocysteine levels interact with the effect of B vitamin treatment? You would sort of anticipate that the higher the homocysteine level, the bigger the effect of the treatment. That's exactly what we found. So this plots the, I haven't given you the individual points because there's too many, the rate of atrophy per year on the vertical axis. Look first at the blue line. These are the people who received placebo, and that confirms very nicely the previous slide I showed, where in normal people, or in these cases they've got MCI, the higher the homocysteine at baseline, the faster the brain is shrinking. And you can see it's over a huge range. It ranges from 0.5% at the lowest level of homocysteine to 2.4% at the highest level of homocysteine. But what happened in the group that was treated with B vitamins? It's flat. The B vitamin treatment abolishes the relationship between plasma homocysteine and atrophy. So any atrophy that's occurring, and of course there is some in the treated group, is not due to homocysteine. Just show you a couple of examples which turned out to be fairly extreme, but they're genuine. This is an MRI scan which is a subtraction scan where the scan done at baseline is subtracted from the scan 2 years later, so you can see the change. And the change is shown in a color code, and blue indicates shrinkage of the brain, and the brighter the blue, the more the shrinkage. So those sort of turquoisey pixels around the ventricle, voxels around the ventricle indicate a shrinkage of 1 millimeter, which is quite a bit. The average rate of atrophy for this person was 2.5% per year, which is pretty high for MCI. It's almost in the Alzheimer, it is in the Alzheimer range. Oh dear. I'll rush through. Have I got 5 minutes? Thank you. I'm showing you this because this person's homocysteine at baseline was already quite high at 22, but over the 2-year period it went up to 30. And when we decoded, he was on placebo. This person had a homocysteine at baseline about the same, at 24, but his homocysteine went down to 12 after 2 years, and when we decoded, thank goodness, he was on active treatment. And you can see the atrophy rate for this person was 1/5 of that for the other person, and there's only a little bit of blue showing around the ventricle there. So we've shown the treatment lowered plasma homocysteine, slowed brain shrinkage. What about cognition? I haven't time to show you the results, but to summarize them, we were quite delighted to find that the treatment actually slowed cognitive decline in a subgroup, those with high homocysteine at baseline. In 6 different cognitive tests, it slowed the decline in all 6 tests significantly. So what we believe is happening here, that's a warning, isn't it? What we believe is happening here is that the treatment, the B vitamins, lowers plasma homocysteine, which reduces the rate of brain shrinkage, which reduces the rate of cognitive decline. So what are the outcomes from the trial? Well, B vitamin treatment in people with mild cognitive impairment slows brain atrophy by up to 53% in those in the highest homocysteine. B vitamin treatment also slows cognitive decline, and I haven't shown you, but it improved the clinical outcomes, actually improved them. Ladies and gentlemen, I believe these results show that B vitamin treatment is a disease-modifying treatment. It slows down the disease process. But I point out these responses only occurred in subjects with a higher baseline homocysteine, above about, sorry, micromole it should be. So when you convert from one slide to another, 11 micromoles per liter. So the big question here today is, since improving the methylation status can slow the disease process in Alzheimer's, what will it do to the development of dementia in Down syndrome? I cannot predict it, but I think it's a question you should consider asking yourselves. So here are the factors that I listed at the beginning that might modify the development of dementia in Downs, and I believe it should be possible to modify the disease process. And here's the Bill Mobley slide. I'd just like to point to the gaps because I'm running out of time. I think we need more animal experiments for sure, but we also need urgently larger and better planned clinical trials on nutritional factors, on exercise and enrichment. Because, as Mara showed, these non-pharmacological interventions seem to be working, and they're much easier to do, much safer, and much more patient-friendly. But they will interact with drugs, so we will need to do things like enrichment together with a DYRK1 inhibitor, for example, as Mara pointed out. So finally, ladies and gentlemen, let's share this optimistic view of Kathleen Gardner, expressed last year in a review. Down syndrome is due to an extra copy of human chromosome 21 and has often been considered too complex a genetic abnormality to be amenable to intervention. However, she says, recent successes in rescuing learning and memory impairments in a mouse model of Downs suggests that this negative outlook may not be justified. I hope you agree with that. Thank you very much.
I think we have time for a couple of questions.
So could you go back to the quadrangle?
The matrix.
Yeah.
That one.
How do you know it doesn't go the other way?
Starting with what?
Starting with treatment, leading to plasma homocysteine, leading to changes in cognition which secondarily impact brain volume. You know, these are just correlations. We don't know. I mean, I love the data.
Well,
and I love the correlations.
I hope he doesn't mind, but our wonderful statistician, Abrim Ulaj, we challenged him with this question, and he's using a statistical tool called mediation analysis.
Okay, that sounds very impressive. What does it mean?
Well, it means you can work out which factor is actually mediating the end change. So we asked him, you know, does brain shrinkage mediate the effect on cognition? And I hope he doesn't mind me saying the answer is yes. So I
hope you don't mind me saying I wonder how you know that. But in any case, it's wonderful. And the point is, you're right. The mechanism is yet to be explored.
Well, but it makes biological sense.
Of course it does.
You know, hippocampal atrophy related to memory problems.
And we know that now, that biological sensibleness is something we've known maybe over the last decade. But really, B vitamins might do a great deal more than plasma homocysteine and any number of other things, including direct effects on cognition.
Absolutely. No, I'm not denying that. But your question was, does the change in cognition determine the brain atrophy?
Yeah.
And I find that a bit hard to believe biologically.
Well, do you?
Yes.
You don't know that, I mean, in fact, using one's brain, engaging in intellectual activities may well have impact on brain volume, axonal volume, for example.
Sure.
Anyway, I don't dispute it, I just don't know how we know it.
Yeah. We don't know for sure.
Other questions? Wow.
The vitamin pessimist will suggest that you're using highly toxic doses of vitamins. Was there any evidence of any toxicity at all?
No adverse effects, and we checked for neuropathy because the regulatory authorities were a bit worried about us giving 20 milligrams of B6, so we did a standard vibration test, and there was no statistical difference in the treated group. It looks as if they were tending to get actually less neuropathy, but that's not statistical. They're not highly toxic doses, no. The B12, you know, it's impossible to get a toxicity. I don't know whether anyone has done an LD50 on B12. They may have tried, but I mean, it's a very non-toxic compound. It doesn't mean to say it's not harmful in high doses for particular reasons, like if you have a leukemia or something. But folate at 800 micrograms is not considered harmful. The safe upper limit in America is 1 milligram. And I can tell you that children under 4 in America are actually getting more than 1 milligram by various foods and supplements. So maybe that's not a good thing. But I don't think the doses we used were toxic. Do you, Helga?
No. The question here also in terms of when you come to that situation where they are starting to lose their memory, our concern about the potential growth of cancer is very
David, don't you think that brain shrinkage in this case is more related to vascular mechanism than to beta and tau protein? And that we might need in Down syndrome to think about another approach to, let me say, not to lower homocysteine, because homocysteine is usually low in Down syndrome, but maybe to lower SRH?
Yeah. No, you asked two questions there. Do I think it's related to vascular? I'm keeping an open mind on that, because another positive trial of homocysteine lowering is in age-related macular degeneration, which is almost certainly vascular. And that worked. These B vitamins reduce the risk of macular degeneration. We also know that there's white matter changes in the brain in the elderly that are related to cognition, and it could be, but it hasn't been proven, of course, that the B vitamins partly reverse that. What has been shown is in people who are B12 deficient and have massive well, I call it white matter damage, they can reverse it by giving B12. So, you know, the traditional view of the radiologist is that person's got, you know, serious white matter damage, that's it. It's not true. It can be reversed. So I'm keeping an open mind as to the causal link, whether it's that or whether it's a kind of neurotoxicity. And I carefully didn't mention amyloid. I think tau may be possibly involved. But anyway, that's another question.
So there are many questions. The problem is that we are running out of time. We need to go for the roundtables also. I think this will be also very, very important. So I think we can have one last question.
Hi, I'm Shen Smallwood. I'm a parent of a child with Down syndrome. And I also set up a local charity in the town where I live. I met Dr. Stacey here because Dr. Stacey lives in the same town as me and has a child also with Down syndrome. And Dr. Stacey presented all her research and information about the things she found out. And so from there, I further developed the, well, obviously Dr. Stacey's skill, one of her skills is in exercise and sports medicine and nutrition. And from there, Essie taught me how important exercise was, how important nutrition, but not just, you know, a little bit of supplementation, good quality nutrition is, and the importance also of music, how much music has affected our children's brains, you know, and how much enjoyment they've received out of that. So since then, in the past 3 years, I've set up a load of different activity programs to give children the opportunity to experience and to get, you know, lots of exercise, excellent, you know, nutritional supports, and we've seen by comparison how much difference it's made in the short space of time that we've been running these programs, and, you know, and how it's going from strength to strength, and how these children are making fantastic steps. And it's really so wonderful and encouraging to see that it just really continues to encourage us on and, you know, working more.
That's absolutely fantastic, isn't it? I mean,
can I just say one thing? Sorry. Yeah. I think it's Shen does herself down because she has actually. I gave talks and we had, you know, families in our living room, etc. And she's taken that and really run with it. They have swimming programs 3 times a week. They have music, Suzuki music lessons. They have speech therapists, etc. coming in. But what we do have huge battles getting, whether it be PCTs or whether it be pediatricians to listen. So it's been fantastic to hear that environmental enrichment plus EGCG and fish oils, I know we haven't mentioned that very much, improve outcomes. The difficulty we have is if we go to a pediatrician and say, can we have a vitamin profile done, please? Yeah. The answer is no. Yeah. We're fighting. We get the pediatricians now will measure zinc for us because about half of the children that we have down there are zinc deficient, but getting anything else done is a real struggle. What would help, I think, Peter, is if we can have clear summaries of the outcomes from this day, which are, you know, bound and glossy and everything, so that each parent actually can take that to their paediatrician and say, yes, these are our clear sort of summaries. Okay, the stuff that we're still arguing about, fine, but we have here environmental enrichment, we have some clear messages about certainly the B vitamins, things that are not going to necessarily do any harm if they're given to our children. At least we can check those levels. We've got to start at the basis of checking the levels in our kids. That is a huge, huge struggle. And I'm a doctor, so for me to ask another doctor, could you please check the levels, and they're saying no, we've got some really fundamental questions to be asking.
Should we pick this up later? I mean, you've said so many fantastic things, I would love to pick them up.
But I would say an important thing to say is this has not been tested in people with Down syndrome.
Not at all. No.
There's a very real possibility, if the hypothesis is correct, as shown there, it won't work, right? So the exercise, great, all that stuff is great. But please don't carry away the message that because we're enthusiastic about this information in one context, that it'll apply to all of the contexts. We have to be very careful. The last thing we want to do is take an optimistic message forward that's not well founded on data. So I think you have to be careful.
I entirely agree with Bill. Why I showed this data, Peter asked me to, was to show that disease modification is possible in a similar situation. But as Bill says, you can't extrapolate it to Downs. You have to do a study.
I mean, I'm excited by the idea that if it was, I'd love to do the trial in Downs, because if it's true, it's a blockbuster. And why? Not just because it's disease modifying, because it directly tests the relevance of the homocysteine level. For all I know, normal levels of homocysteine aren't low at all. Right. Well, we'll see. We'll see.